Hi, welcome everyone. This topic is on fasteners and holes. My name is Tyson Lee. I'm a mechanical engineer and a mentor at 3309. I just want to thank 5199 Robot Dolphins for inviting me to give a talk on this subject. We're going to go over machine screw sizes, different screw heads, holes and drills, and how you make those holes using a drill, and how you might tap that hole, and why or why not you may want to use a nut and rivets. Not my personal favorite, but it's got to be covered. So what is a machine screw? On the right-hand side here, you see a bunch of these screws. They're called nuts, bolts, fasteners, whatever you want to call it. They're a little bit different than a wood screw in the sense that the wood screw is meant to be self-tapping into, obviously, wood. And these fasteners are really meant to be fastened into nuts or threaded holes. They really have to be matched to each other, the screw to the nut. There's inch and metric standards, and they're defined by this type of thread chart here, or this thread geometry. Don't worry about seeing it or reading it too much, but just know that it's a very specific geometry that it's defined by. There's standard inch and metric screws. The way that they're described is very different as well. The inch threads are threads per inch. So if I were to take an inch distance here and count the threads, it would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that would be 10 threads per inch right there. On a metric size, you'd actually describe it by the distance between a thread, and then you start off with the major diameter by measuring the diameter of the screw, the outside of the screw thread, and that's the major diameter. So if this was 3/4 of an inch and 10 threads per inch, that's a 3/4 10. On a metric, it'd be an M25 by 2.5. A little bit very different than how you would express it on an inch thread. But don't worry, 95% of the screws you'll ever use here are inch. But good to know that the metrics exist, so watch out for those. So in every shop you're going to see a tap chart or a hole chart here, and we'll just start on the machine screw sizes on the left side here. The numbers are going to go from 0 to 10 or 0 to 12, and by the major diameter, it's going to go by size. So it doesn't really correspond to anything, exactly to the decimal size. It's just a standardized diameter. And then after 12, it goes to 1/4 inch. And then, of course, there's larger than 1/4 inches. But generally, you're not going to see anything larger than a 1/4 inch or 1/4 20 or maybe 1/4 28 thread in FRC. For each thread, there's also a thread size. There's also a coarse thread pitch and a fine thread pitch. And you'd express that as 1024 or 1032. By far, there's 1032s are used on FRC size robots. It's just a good sturdy size to use. Sometimes you might want to use a 1/4 20, and then go down to an 832 or a 632. And there's only like one instance that I can think of that you'd have to use a 1024, but you don't want to keep those two together. It's a recipe for disaster. And then just know that 440s, they're pretty small, but they're very commonly used for electrical boards. Lots of other sizes exist. The whole point here is to limit the screw sizes available to you, or there's lots of screw sizes available to you, but you want to limit the screw sizes that you actually use to help standardize your screws. And it's going to be a common theme moving forward here. So screw head types, lots of different screw head types. There's no other reason, there's no other way for me to explain it, why there's so many different screws. You're going to see architectural, automotive, carpentry, and there's just no other reason other than various uses in history. So we're going to use a hex socket, so 6-point, because the actual hex driver that you use provides really good torque and a non-slip torque. And because we've standardized these screw sizes, we only need several hex driver sizes. So if you only use 1032s and quarter 20s, then actually it becomes really simple that you only need to use a 1/8 driver or a 5/32 driver, and that would be a blue and a red. And makes it really simple to work around the pits and kind of you really get to know the screws, and hey, I need a blue, hey, I need a red. That's really going to be simple to use in the pits and putting the robot together. Phillips head are still used, these 4 points here, and flatheads like this, but really try to use a hex head because it's just a lot more firmer. I'll talk about flat and countersink screws a little bit later. So when you specify a screw size, you talk about the thread pitch, and then you have to talk about the length. So the length is the length of the screw right here from underneath the head to the length of the threads. What's a little bit different about a flat or countersink screw is that you actually measure it from the material, the top of the head, to the end of the screw. So really what's inside the material is what the length of the screw is. So you'd express it like a quarter 30 or 1032 by 3/4 inch, or 0.75, or quarter 20 by 1 inch. And the other thing that I want to point out about when you need to use a countersink, you have a minimum plate thickness that you have to be using. That plate thickness has to be the head of the thickness of the head. If you use a cap screw, then you don't need to worry about that. You can use as thin as you want or as thick as you need to. And then just another warning: please don't force a screw into a nut or a thread. If it feels tight, check to see if the thread is correct. Something's cross-threaded or in the threads blocking the holes. The screws can break very easily and cause just a big problem later. I'm going to gloss through this slide really quick. There's a lot of good engineering in here, but I think it's just a little bit out of the scope of this discussion. What I want to show is that what I really want to stress here is that you don't want to torque it too much, and you don't want to torque it too little, or else it'll just fall out. So how much you really torque it to? Just give it a feel. It's very much a feel between a 1/8 to a quarter inch turn, past finger tight. I've always called it German torque. It's good and tight, and you kind of get a feel for it as you keep going. This is another funny slide to me. These are all the type of specialty screws that you can think of, but really none of these are real. These are all just a bit of a joke. This offset bolt for mismatched holes. When you think about it, a screw just isn't going to work when you look at this screw, or even this one looks just really funny because the hole is too near the edge, right? I mean, these are all the problems that you could come up with when you deal with the holes and fasteners. Even though the fastener looks so simple, there's lots of reasons why, lots of ways for it to go wrong. So like I said, you can't talk about fasteners without talking about holes. Every fastener goes into a hole. Holes are made with drill bits. You've all seen these drill bits before. You put them in a hand drill, a drill press, a lathe, or a mill. Drill bits are tightened in the chuck or a collet on a mill. It's nice to have a full set. I'll admit that it's really nice to have every little fine drill size available, but you don't need all of them. If you want to know what the drill size is, it's always marked on the end. If you can't read what's on the end, then you just use a caliper. The size of this shank is always going to be the size of the size of the drill bit, unless it's obviously not. So all those drill bits there are charts to show everything about every size of a drill bit, and there's lots of them. There are standard drill sizes of numbers, letters, and fractions, but what really matters is the decimal equivalent. So smaller the drill, the larger the number. So there's really tiny drills, and there's even tinier drills in this side for sure. But then when you get up to about a 1/4 inch, it goes to 1, and then it jumps up to letters, and then it goes to letters. It'll go to fractions. It'll just simply go to fractions. So why are there numbers? Why does it start with numbers? It's just because at really fine divisions, it doesn't make sense to do anything other than it doesn't make sense to have fractions. You couldn't really have these fine divisions of an 039 and an 040. Then you throw in metric drill bits. Then you have all these drill sizes to think about. But good news, we only really need to drill to have holes for a very few sizes. So back to this chart. You're gonna drill. You're gonna, for every screw fastener, you're gonna you need to create a clearance hole. Now, this is why you have clearance. You need to have the hole size larger than the major diameter of the screw, and that's always going to be, the hole can't be smaller than the screw, and of course there's different ways there's different standards. Either you want to have a close fit or a free fit or a normal fit. I mean, you go into SolidWorks and you'll say, I want a precise fit. I'm going to say, I mean, this is my big point here, that a tighter fitting hole does not mean you'll get a more precise fits, because you need those clearance to fit the parts, and not everything is or can be made precise. The tighter the hole, if you tighten the hole too much, then the parts aren't going to fit. Then you go ahead and you try to assemble your robot, and you're going to end up drilling the hole out anyway, and then you lose your precision that you put into the locating that hole. So obviously, a grossly oversized hole isn't desirable either. So out of this chart, I would recommend a free fit here. And there's going to be a good reason later too. So for the 1032, you don't want to use a number 7 201 size to drill a clearance hole. And again, because we standardize these screw sizes, we only need to have these 3 screw sizes, three drill bit sizes. A little more into the drill anatomy. I want to point out that a drill bit isn't pointy sharp. If you actually take a really large drill bit, you'll look at the end of it, and it's got this what's called the chisel edge, and it's very well defined as to how it creates the cutting edge to the edge here. This cutting edge is really where all the work gets done. It's because theoretically at 0 here, it's got 0 speed, so it's not going to do any cutting. So they put that chisel edge in there so that you get it to a point where it can actually start to do the cut. Now, that chisel edge is actually what makes the drill bit walk away from you when you try to do the first drill. So I'll talk about, so you always want to do a pilot hole or a center punch to get underneath this chisel edge here. So how to drill a hole? Scribe a line or a crosshair where you need to. Because this is an online, I can't. Normally, I would show this would be much more of a hands-on demonstration, but scribe a line, center punch or center drill using a mill or a lathe, and pilot drill a smaller hole. I recommend an 1/8 or 3/32. You should have plenty of these available. They're really cheap. They're plentiful, and you consume them really quick. And then you can just go ahead and go to the final drill size. When you use a drill press, it keeps it nice and vertical and rigid. But most often, a lot of times, you're going to be drilling by hand. Some things to keep in mind is to keep that drill bit perpendicular to the surface. Don't bend the drill bit. So drill bits don't like to be bent. They don't like to be going sideways. They're not strong. They're not strong radially. Every time you bend a bit while you're drilling, you're essentially flexing it like a plastic spoon, and that little thin drill bit is not going to last. And then don't clog the flutes with material. Frequently back it out, blow off the material, and it'll definitely cut a lot better. And of course, it'll cut a lot better with when it's lubricated with metal. If you think it's not cutting, and just throw it away, because you always want to wear safety glasses when drilling. Bits break so easily, and when they break, they go flying, and that very possibly it can go flying right into your eye. Just throw away the broken bits. If you break a bit, just throw it away. Don't try to put it back. Please don't try to put it back and think that you're ever going to use it later. You won't ever absolutely throw it away. So now let's go back to this tapping chart, and let's look at this middle section here. So to tap a thread into a part, you also need to drill a hole to clear most of the material out. So the size of the hole is going to be dictated by what I talked about earlier, or what I tried to show earlier about this minor diameter. So the minor diameter of a 1032 is 151 or 152, and for aluminum, which is mostly what we're going to cut here, or cut in robotics, you want to use 75% of the thread. So if you do the math, that between 152 and 190, it's going to be 75% of that is the 159. So that's how this drill chart gets created. So you use this 159, and that 159 is a number 21. So instead of writing on the drill bit or stamping on the drill bit 159, you're gonna stamp 21. It's gonna be stamped 21. You're gonna go and find that 21 and use it to start this the tap hole. And then you put in the tap, and then you can cut the rest of the material away. Gun taps are pretty much standard. They're two flutes. They're long lead in. The tap through for tapping through holes and plates and extruded tubes. If the part is thick, you can make a blind hole. You can actually make a blind hole, which means it has a bottom. It's not all the way through. But when you do that, you really need to use a bottom tool, a bottom tap, to finish that last thread. Because what's going to happen is if you try to keep that gun tap in there, it's going to bottom out and it's going to break. You definitely want to avoid breaking taps. So let's look at this again. For 3 different screw sizes, an 832, a 1032, and a 1/4-20, we only need to have actually 5 screw sizes, because this number 7 that we use for tapping a 1/4-20 is the same number 7 you're going to have around to create that 1032 clearance hole. So it's a really good reason another good reason to standardize these hole sizes. And if you actually have a large fractional drill bit set, you can use the 1364. It's really close. This number 29, a 136 is very close to a 532nd. So for 3 screw sizes, we only need 5 drill sizes for tapping and clearance holes. Order all 5 of these. Order lots of them. You're going to go through a lot of them. So how to tap a threaded hole? Look up the correct tap drill size on chart. Drill the hole. Follow the previous steps of drilling a hole. Use a tap handle or drill you can put them in a drill. I recommend it if you're doing thin, only if you're going through thin material like a thin plate or a thin tube, and use plenty of lubrication. Keep that tap perpendicular. The ways that we do it is you have a spotter. So say you're looking in this perspective, you always have someone on the side to tell you if it's up and down, perpendicular. Another thing you can use is a tapping block. I hear Code Orange actually uses that often. And again, plenty of lubrication, Tap Magic and WD-40 if you don't have anything else around. Clear those chips out often. Back it out, and don't ever try to don't ever try to overpower that tap. If it feels too tight, back it out, check for any issues, or risk breaking that tap. Because if you break that tap, it's real difficult to remove. It's not impossible, but you just want to avoid it. And you break a tap that's totally usable for later, and you may not have any more taps around. So, machine nuts. At a real basic level, machine nuts are just like small plates with threaded holes, and they're already tapped and easily replaceable. So, you know, it's really easy. It's really, you think it's really helpful to use instead of having to tap lots of parts. So, you know, I'm not against nuts. You can use them for high strength areas. Nylocks are actually having nylocks offers a really big advantage. You can use them when you have thin wall parts, for, you know, it's like 16th wall plate. You wouldn't ever think about tapping a 16th wall for a 32 thread. And sometimes you want to avoid having to tap into plastic. I'm not saying it's impossible to tap into plastic, but there's often a lot of good reason not to tap into plastic at times. But when you think about how to use a tap or use a nut, you have to consider how we do it on our robots. You have to consider the fastener length. So it has to go all the way through the tube of the has to go through all the way to the tube and the thickness of the tube. And then you have to worry about having tool access. So your wrench or your socket, you have to start designing around that, whereas all you need to worry about on a tap screw is having just the driver being able to drive it in. And a little more engineering principle here is that if you look at this, when you use a bolt, a nut and bolt here, you actually have two plates now that have clearance that are necessary, that I talked about being necessary earlier, but now you start to have a little bit too much clearance. You have 2 times the clearance for a normal hole. So then it starts to get a little bit more sloppier. And you probably want to consider other means to precision align those holes. So rivets. Compared to screws, they're cheap, they're lightweight, they don't require threads or nuts. You can just drill the same size drill on both parts, and you're good to go. Whether they're stainless steel or whether they're aluminum, they're still going to be weaker. And so because it's a weaker fastener, you definitely want to put more rivets on a typical part than you would if you just use a screw or an aim in a nut and bolt. But they're easy to fabricate, 2 holes in a thin sheet of metal, easy to drill, and when they do wear out, or you can easily replace them. Just keep in mind the reason why you would want to replace them is because they weaken over use. Because how it works is you have this stem here, and you push it through the hole, you push the rivet through the hole, through both holes, and then you take the tool, and right here, it's gonna pull on this stem here, and it's actually gonna pull away on the material here and deform this whole area so that it makes it larger than the hole from the blind side. That's why they call it blind rivets. And then at the point that it's fully deformed, it'll pop off. And that's, again, pop rivet. So you get a nice little bump around here, but that's not forever. You can't really rework this. You can't tighten it back up. You can't take it out and replace the nut. It'll weaken as it gets used. So really, if you're going to use rivets, consider a replacement schedule or a check. Tons of broken rivets on the field after every match. And then there's standard drill sizes. You use the 5/32 or a 3/16 or a 1/8. But the problem is, it's very easy to leave this to swap out the size, put it on a table, and not put it back, and then it gets lost. They're really tiny. Don't lose these. Make it a habit to, once you take it off using the tool, put it right back. That's why every rivet gun has a place for each one of them. So we've talked about fasteners, we've talked about tapping holes, we've talked about nuts, we've talked about rivets. So which one would you use? And I can't say it, there's no blanket statement for this. The use of a rivet versus nut or a hole tapping, it's highly dependent on your design choice, your load requirements, the material availability, and your fabrication resources, whether you just have a drill press or a CNC machine. But let's go over some examples of how you would actually design this particular vacuum climber. So let's look at this area right here. So if we wanted to put two plates together to sandwich the tube, very easy to do with rivets. You just make those holes and you pop those rivets, and you can use it with basically with really lightweight thin walls. You can do pretty much the same thing with thin walls and bolts and nuts. So if you don't have a pop riveter, and you can just use the same thing with bolts and nuts here. Now, if you needed a little extra strength here, you can actually thread the other side of the plate. So now you don't have a nut here. You can thread all the way across. And then if you have a thicker wall here, you can just tap the walls of the tube, and it's commonly done. And let me skip back over. And it's commonly done here. And so now you can actually have a thicker tube and a thinner plate. What's best? All these examples are okay. Each one of these could be further optimized for sure. Like on this example, okay, we needed a larger tube to accommodate the weight of the robot. Well, then we can lightweight it without losing a lot of strength. And that's going into an engineering principle. That's way beyond the scope of this. So that's my last slide. Let's see if there's questions here.
Yeah, we do have a couple questions from the chat. I will read a couple of them out. From earlier in the presentation, I think when you were talking about screw hole clearance sizes, Fernando asks, what's the difference between a number diameter and a fraction diameter? I believe he was referring to quarter 20s versus number 10s. And
right. I mean, yeah. It just seems to stop after the screw sizes are very standardized. So our 10 would just is instead of saying 190, and you just say 10, right? And if you wanted to go a smaller size, you can't. There's not every infinite numbers of screw sizes. So they're very standardized in terms of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12, and it stops at 12 because at that point, then fractional sizes make sense. So you really want to focus on the decimal equivalent, but you wouldn't ever. I don't say I need a 190 32 unless I'm making an engineering drawing for work, and that's a different story. So that's why there's numbers, and that's why there's fractions.
Okay. We also have. Let me see. Eli asks, if you need a bolt larger than a quarter 20, what size or sizes would you recommend? Someone else in chat did recommend a 3/8 as well. So you have that for your information.
Sure, but there's also a 5/16, and then there's also 9/16. I mean, it really just depends on how big you're really going. I mean, an eighth of a half inch bolt, I don't know. I couldn't imagine where we would need that on an FRC robot. It's so strong. That's where I'm kind of saying is that a quarter 20, man, a quarter 20 of the strength of a quarter 20 is so strong that you don't want to overdo it with these.
Okay, and then there was also a question that if you have to go larger than that quarter 20, which obviously you said doesn't normally happen on an FRC robot, what thread size would be recommended? Higher thread density or lower thread density? Oh,
I mean, for a larger screw thread, yeah, you start to get more into the coarse, and you've kind of noticed here. I didn't really talk into why are there 32, 32, 32, but for a 632, it's coarse, and an 832 is also coarse, but then a 1032 is also fine. It is now fine. This gets into a much larger, much more technical definition of why and how in terms of strength. Honestly, if you're going larger than a quarter inch, you probably want to start looking into the coarser threads. That's why the quarter 20. I would recommend a quarter 20 is a lot more common than a quarter 28. Not that the quarter 28 is impossible to use, but the tap size of a quarter 20 is actually a lot more easier to use than the tap size of a quarter 28. It's really too extra fine. When the threads get really fine and small, then that's when you start to want to use opposite. When the threads get really fine for being large, you kind of want to avoid those fine threads.
That sounds great. Jacob from Code Orange asked, what drill and tap chart do you use? And we can tell he's from Code Orange by his wonderful profile picture of one of their last robots.
So, I mean, there's a tap chart in every shop, and you're going to see a tap chart just like this in almost every shop. But the point is that you can use any tap chart. These names might, these descriptions might be different, but just know that if you only standardize these screws, you only have to use 3 different sizes here. Or 3 different sizes on the tap size, especially if you're using aluminum. So really, they're all going to be the same because they're all based off of a mathematical standard and the machine design handbook. And there's proofs for all these, and it's an upper level class that actually I'll admit that I dropped because I found it so boring. Because right here you have all the information already done for you.
Okay, it looks like we have 2 more questions, unless there are any more that are going to come in very soon. Todor asks, is there an easy way or rule of thumb that you can use to decide when to use various sizes of bolts or rivets?
I would say most generally just use a 1032. I mean, even though I talked about using 832s and even a 632, I could very easily argue that an 832 you could build a whole. You can just use that to build an FRC robot. Most robots aren't going to be like that. So a 1032 is so common. The hex bit is really easy to use. You can go between a button head and a cap screw really easily, and it's just really easy to use for at a 1032. At a quarter 20, I wouldn't even recommend a quarter 20. I know the kit bot comes with a quarter 20 screw size or nut and bolt size, and I know it's easier to use, but you almost have to design around how big that screw is, how big that fastener is, and the head is, and then even the screw, the nut access. So that's why it's just kind of converged onto a 1032. It's just proven to be a really good standard screw size, and you can only bring so many screws with you, and so it's not just the screw size, it's the screw length. So now you have to have a bin of every screw length of a 1032, 832, quarter 20. So if you just try to focus and standardize your fastener size to a 1032, I think you'll be fine.
Okay, and we did have a couple more questions come in since that last answer, and a lot of them are relatively related. I'll start with our most recent one because it's sort of related to that last question. Rick asks, do you recommend threading into aluminum plate or using a steel nylock nut?
Depends on the plate. Depends on how thick that plate is. It was kind of a debate I had with a friend of mine, another mentor of mine. I worked at 968, and I'll be honest, I wouldn't have a second thought about tapping into a 1/8 inch wall extruded tube here. We do it all the time. I've always done it a lot of times, but if you really want to have that higher strength, you actually wanted to use that nut, and you can probably use a lot less of these fasteners. So if you have the size of it, that's okay. Then now you can just tap into it. But if you need to use less fasteners, then you can start considering using the nut. And it's also design dependent and what you can get away with, but definitely not less than a 16th, or definitely not a 16th, and 3/32 is actually what's shown right here, or 3/16 wall is what's shown here, and you can kind of see it's really chunky compared to this 1/8" wall here.
Great, and we did have another question from Rick come in. When do you use a button head versus a socket head?
That's a good question. And it's kind of funny, to be honest. It really doesn't matter. There's a technical answer to it. A button head has a lower head height, and that alone might be advantageous. But technically, the reason why it has a lower head, or what happens when you have a lower head, is that you actually have a larger surface to get enough friction. It's this slide that I kind of glossed over about friction and clamping force. But the real answer is it doesn't matter, and button heads look better. So a lot of times we use button heads, to be honest.
Great. Okay, and then we have two other questions that are very similar to each other. First one is from Angel. It asks, for a joint that needs to be strong, like on the drive base, would it be better to use bolts in a gusset or weld the joint? And I guess you could extrapolate that to bolts or rivets in a gusset, or to weld the joint.
Look, I know teams use rivets on dry bases. It's something I wouldn't consider at our level. It's definitely doable to use bolts and rivets. Hey, top teams have done it. I know they do it. I don't think they're using aluminum rivets. So whatever stainless steel or steel rivet they're using, you need to have an appropriate driver for it. But at the end of the day, for a drive base, I go welded if you have the ability. But again, I haven't even talked about welding in terms of joining parts here. There's definitely a way we could have definitely welded these parts together as well, and that would be the ultimate strength.
Okay, and then another one on welding is from Todor again. Are there any pointers you could give on welding, when to use or not to use, etc.?
I think a drive base is really good for welding, because once you've defined that drive base, you want it held together tight, and that's a really good application of having a welded structure. Then you get outside of then you get in an FRC robot on an FRC season. Now you're talking about modularity, where you don't necessarily want to commit yourself to a certain design or a certain fabricated part that's completely welded and you can't go back onto. So after the drive base, I'd be totally I wouldn't consider too many other things being welded, except unless you're doing a situation like, I wasn't on the team at the time, but 309 when back in 2018 or Power Up, they had the Falcon Door climbers, the two buddy climbers. They had to weld that chassis because of the loads that they had to consider. So I understand that for sure. And so it really is design dependent. I'm a lot on our team. We have a welder. We have we've trained the welders, student welders, and so that's part of our training and what we have capable to us. But I know that not every team does, so I wouldn't have to go to welding either.
Great, and we have two more questions. They both relate to some aspect of riveting. The first one is from Angel again. It's, would you recommend using rivet nuts for structural purposes?
I'm glad that rivet nuts were mentioned. I was going to put a little slide or a little line right here and say, hey, I recommend rivet nuts. I don't know how that, if you were reading my mind here. So what a rivet nut is that you can actually rivet a threaded fastener here, and that would that would be the tapping, that would act like you're tapping into the plate, and now you can use a fastener to bolt it on and off very easily, and take it off on and off very easily. I do recommend it. There's definitely a use for it. You have to consider the extra space or gap that gets occurred, or countersinking, or the special rib nuts that are countersunk. But then again, like I mentioned about countersink screws, you have to consider the thickness of the plate. And at that point, then I'm not sure what you're gaining by how thin of a plate you're using. But I guess I forgot to mention that the drawback of having regular rivets is that you can't easily take parts on and off together without drilling them out and enlarging the hole. So you don't want to use rivets where you're going to take parts on and off frequently or potentially. So rib nuts allow you to do that, and yes, I'd recommend it. I didn't want to get too far into it when I had a line. I actually had that line right in here, but it's too much to explain throughout the whole, considering the breadth of the information.
Well, I'm glad we were able to touch on that. It looks like we have one last question. It's been a while since any more ones filed in. Eli again asks, do you normally use full steel rivet or aluma steel rivets with a steel mandrel and aluminum head?
I'm not the rivet expert. I quickly share that I don't really like rivets that much, so I don't have that much. Honestly, I don't have that much experience with them. But typically, they're going to be aluminum that we use on our robots. Is going to be aluminum. I think all aluminum. They pop off a lot easier, and they're just a lot easier to work with and not having the hand riveter. There is a Milwaukee M12 powered cordless riveter, and we got it last year, and it's amazing. It's amazing. Now that actually is starting to make me like rivets. I would recommend, if you guys are thinking about using rivets, throw this or put this into the lower shelf here and buy that Milwaukee M12 riveter. It's amazing. I can't recommend it enough. It's making me like rivets, but I just haven't used it that much.
Yeah, well, I certainly love a good pneumatic riveter myself. It looks like that was the last question. Thank you very much, Tyson. I'm sure all your information was extremely informative to a lot of our rookie members and teams, and I'm sure even the most expert of teams learned a little bit from this presentation. We'll be back here tomorrow with 2 more workshops for you guys. Tomorrow we have motors and gearboxes with Team 5199 at 5 p.m. And you can learn from some of our past mechanical leads about how to choose motors and gearboxes for different purposes and uses. And then at 5:45 p.m., we'll have Teams 3309 again, Code Orange again, and 5199. And that will be a panel from our Woodie Flowers finalist mentors on mentoring to make a competitive team. You'll be able to learn from our Woodie Flowers finalists with years of experience about how their mentorship helped grow the competitive aspect of their teams. And we're super excited to hopefully see you guys tomorrow. Thank you all for tuning in and dealing with us during our technical difficulties. Thank you for that chat suggestion. And we will see you tomorrow. Thank you all very much, and we hope to see you again.